Good morning, good morning. Even before HCTV, back of your spirals. I'm so sorry. I meant to have this up as soon as you came in, but then my chairs were all messed up.
So 1.3,
Yes. 1.3 multiple choice practice. Or 1.3 APNC. AP more. Alright, cool kids. Try it on your own first. Let's see how we do. Three questions, I'll give you 4 minutes. Then I'll play HCTV. They're in the back of their spirals. Section 1.3 APMC. You guys should be close to having attempted them all. One last minute. Alright, I'm going to go ahead and get HCTV going. You guys might still be finishing up an attempt. We'll read it in just 1 second. Uh-oh. Well. I'm going to go ahead and pause the video. The test is on Monday, which means we'll be done covering content Thursday, which means I think your forever quiz is Thursday. Hold on, let's double check. What I was saying is that even though homework wasn't due today, I got distracted. Even though your homework isn't due today, I did advise you guys to get your forever cards all caught up because the forever quiz was coming 2 days before the test, and so if the test is, I think it's on the calendar too. Test is Monday, that would make it Thursday. Your forever quiz is coming up, and oh, look at you guys, I'm so nice. It's on Friday.
Is there 4 or 5 sections?
Sections. 5. We're finishing 1.4 today, then we have 1.5 today and tomorrow. The nice thing is it's infinite limits, which are basically horizontal asymptotes revisited. So you've done them before. It's just going to be a little tricky on some of the AP-ish questions. But yeah, the forever quiz will be on Friday, right before we work on our review, and then the test is on Monday. Good question. All right. Here we go. What did you guys do for number 121? And that was as easy as that?
Yeah.
Yeah, so on the top, when you plugged in, what did you guys end up getting? Just 1 on the bottom? So just B? Everybody agrees negative 1/3, letter 8? So there's 24 minus 25 on the bottom, and it was 8 minus 6 plus 1, so 9 minus 4.
No, it's 25 minus 16.
4 and 2 is 8. 8 minus 6 is 2. 2 plus 1 is 3.
Yeah, that's 3 over negative 9 is.
Yeah, then it reduces.
Yeah.
Oh, gracias. I didn't get the negative 9 at the bottom. Okay, so you ended up with 3 over negative 9 reduces to negative 1/3. That makes more sense. No, you're okay. 122. What did you guys think?
Spooky, but okay.
The first one.
I don't.
Okay, well, I hear some different answer choices, but long story short, let's figure out why the right answer is the right answer. So what did you guys think of for Roman numeral 1?
You plug it in.
Plug it in, what'd you get?
2 over 0.
Okay, so if you get 2 over 0, what does that mean?
Sign check.
Sign check. It's a vertical asymptote. The answer is plus or minus infinity. And according to the book right now, we could check signs. But long story short, what are they going to say with an infinite limit? It doesn't exist, right? How about with number 2?
0 over 0.
Yeah,
0 over 0. So now what?
Well, you can't really.
You can't take the absolute value out.
So I just went on to 3.
You could have, well, no. Couldn't we have tried negative 0.1?
Yeah.
And positive 0.1? Couldn't we have gone from below and above just to check it out?
Okay,
If you did negative 0.1 over negative 0.1, what would you get? Negative 1, right? A positive and negative. If you did 0.1 over 0.1, what would you get? A positive 1. Uh-oh, so if these are positive ones and these are negative ones, yeah, it's a jump. It's a break. They don't agree. So if they don't agree, that one's also D&E. But if you guys want to see, someone I heard say you can't take out the absolute value. Actually, you can.
Huh?
Huh?
No, seriously, sure. Why?
Because every absolute value is really just a piecewise function. Sometimes what's inside stays the same, and that's true whenever x is greater than or equal to 0. And sometimes whatever's inside gets flipped to the opposite sign whenever I have a negative. Now, technically, it can't be greater than or equal to, because at 0, this function does not exist. However, question, does this get you the exact same thing that what I did a second ago gets you? What's this reduced to be?
1.
What's this reduced to be? Do they agree from either side? He's positive 1, he's negative 1 as I come from either side. They do not agree, so therefore, this one does not exist also. When you guys check the sign on number 1, did it not exist anyway?
Yeah.
It didn't exist anyway because the two-sided. We would have had to come from below and above. So it didn't exist for 2 reasons. On the test, you would have answers like positive infinity, negative infinity, and D&E, just a heads up. Does that make sense?
Yeah.
So if they both agree to positive, that's the answer. If they both agree to negative, that's the answer. If they disagree. Okay, number 3. What do you guys think? It's for a similar reason as number 2, but just because I haven't shown it yet today. Remember, you can come from below and above, right? You have to come from below and above as you're taking the limit towards a constant and the piecewise function if there are 2 different pieces. So from below, which one is it? Is it the 3 or is it the 0? Because you think of 1.9 and that fits in the first piece, so that would be 3. And as you come from above, 2.1, wouldn't that go in the second piece? And then that's 0. Long story short, do they agree? Since they don't agree, what do we have to say? I heard some of you say B, but the correct answer was D is in the bond. Anyway, so 123. Ooh, what happens with 123 when you plug it in? Plug it in. 0 over 0, keep going. There are 2, 3 different ways of keeping going. Who chose synthetic division? Who chose long division? Ah, you guys are awesome and you factored it? Or you just skipped it because you were scared of it? Hopefully not. Alright, those of you that didn't know how to factor, question, could you have done long division? We've had 1x to the 4th, 0x cubed, 0x squared, 0x minus 81. Divide by x minus 3. It would have worked. Could you have done synthetic division and put a 3 in the box and had 1, 0 cubed squared? Could you have done synthetic division? Yeah. But how can factoring also help on stack? There is a perfect square in the numerator. So what can we do with x to the 4th minus 81? X squared minus 9 and x squared. Okay. And I can keep going, right?
Hey, yes, another one.
Another difference of squares.
Another one.
Factoring was definitely the easiest way to go, if you saw it. So anybody realized yet that there is some calculus underneath things, but it's also just kind of a lot of algebra,
Yeah.
at least at this point. What do we do now? Remove the whole and then plug it in, plug it in. 3 squared is 9 plus 9 is 18, and 18 times 3 plus 3 is 6. What'd you guys get? Dun, 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 see. All right. Did you guys grade what you needed to grade? Did you correct whatever you needed to correct? All right. Cool beans. Let's go ahead and get back into our notes. We were talking on Friday about continuity. No, Thursday. Friday was Spirit Day. No wonder it feels like so long ago. It's been 4 or 5 days since we talked. But of course you were all thinking about math during Spirit Day.
Oh, yes. Yeah.
Those dance judge tallies, right? There's some adding going on.
Were they doing their
Points totals.
freak out dance moves?
Nah, not that cool. Alright.
They weren't doing that.
You guys should have gotten this page down. Do you remember the definition of continuous?
Yes.
I told you guys to update your forever cards.
Yeah. 80%.
And if you guys noticed, the quiz on Friday is on forever cards 1 through 5. Actually, it might be 1 through 6. But either way, we have the majority. It is 1 through 5 on the calendar. It might be 1 through 6. But we'll see. But coming back, forever card number 4. You guys could have been studying the majority of the forever cards on the quiz on Friday. Long story short, a function is continuous at a point if the following 3 conditions are satisfied. Number 1, the point has to be there, the function has to exist. The limit also has to exist. None of those jumps. Sorry, none of those breaks. Isn't that what we call them, Friday? None of those breaks. Then last but not least, where the limit equals, aka where the function is approaching or intending to go, must correspond with the point. We also talked about the limit from below has to equal the limit from above, has to equal the actual function point. If any of those 3 fail, the function is not continuous. We talked about ways that a function can be not continuous, both removable and non-removable. We talked about common functions that are continuous everywhere. So real quickly, can we remind ourselves of the domain problems, kiddos? If these are the ones that exist everywhere, what are some of the domain problems from pre-cal, from our summer packet? What are some of the domain problems that can occur or that can happen that we need to watch out for?
Normal square roots.
Normal square roots, good. Because with, I'm going to put this in green because it's review, you don't technically have to write it if you think you know it. So the opposite side or the other side of the issue, well, if those are ones that are continuous everywhere, what are the ones that are not? If we have the square root of a function, what do we have to remember for a domain? No. Negative. So that means that my function has to be greater than or equal to 0. Has to be greater than or equal to 0. Cannot be less than 0. What if I have a denominator, f of x over g of x? What do I have to remember?
Cannot equal 0.
Good. G of x cannot equal 0, and we have to remember to factor. Don't go moving stuff to other sides. What if I have any sort of log or ln of a function? Can't be negative, but also can't be 0. ln has a vertical asymptote, so I have to say greater than 0. Sorry, ln or any basic log that's not been transformed. I have to say greater than 0. Other than that, it's up to you guys. I'll try one example. If we had like tangent of f of x, remember tangent has a vertical asymptote, so does cotangent, so does cosecant, so does secant. I'm just choosing one. But remember, if you have a trig with vertical asymptotes, the argument cannot equal those vertical asymptotes, whoever they are. Tangent happens to have vertical asymptotes at pi over 2, and multiples of pi away from that, so positive pi over 2, positive 3 pi over 2, negative pi over 2, negative 3 pi over 2, etc. So for tangent and for the other trig, remember they do a vertical asymptotes, you have to watch out for them. Okay, that was just a quick reminder from the summer packet, a quick reminder from pre-cal. But it's one that might be helpful because the next page says, so watch out for square roots, denominators, logarithms, and trig functions with restricted domains, aka vertical asymptotes. Okay, that works. The next page says, discuss the continuity of each function. Just write them as we go. Just write letter A. Discuss the continuity of each function. Let me go ahead and model it with letter A, because it's pretty easy. So you can go ahead and say letter A is continuous everywhere but at x equals 0, there exists. There actually is a snazzy math symbol that means there exists. I might start using it, the backwards capital E. But at x equals 0, there exists. What type of discontinuity? Vertical asymptote. How do you know for sure? Well, you know the basic graph. That's one way, right? Whenever x looks like this, there's a vertical asymptote at 0. Another way, if you plugged in 0, what do I get? 1 over 0. It's a vertical asymptote point. There's a few different ways of looking at it. The denominator doesn't cancel out, so it can't be a whole. For right now, we'll just say a non-removable discontinuity. If you want to be super snazzy, you can say a vertical asymptote. We're just discussing, we're just talking about the function. He's fine everywhere but at 0. What's going on at 0? There's a non-removable discontinuity, specifically a vertical asymptote. Letter B. What do you guys think? What do we got?
Everywhere except x equals 1, but it's removable. Continuity. So
Yeah, it is removable, it is a whole. How do you know it's removable? Yeah, the numerator can be x plus 1, x minus 1. The x minus 1s can cancel. Another way of thinking about it, when you plug in 1, what do you get? 0 to 0, keep going, right? Continues everywhere but x equals 1, where there exists a removable discontinuity, aka a whole. The grammar was a little better on the second one than the first. I apologize about the first. Letter C. Ooh, this is an adventure. I want you guys to take a second. Can we say continuous everywhere but? Is x plus 1 continuous everywhere in its domain?
No.
Huh? X plus 1, just x plus 1. Yeah, he's a line, he's fine. Okay. He's one of those continuous everywhere ones. How about e to the x? Is he continuous everywhere? Yeah, he is. So what's the only place there could be a problem? E to the x goes on forever.
Oh, what is it?
The only place there could be a problem is at 0, the separator, where they meet. Do they meet, or do they not? How do we figure that out, guys? We could try to graph it.
Plug in 0.
Or we could plug in 0, both. Good. Remember, we could think about as x approaches 0 from below, and as x approaches 0 from above. 0 from below, what am I approaching? 1. 0 from above, what am I approaching?
So,
Anything to the 0 is...
no way.
Oh my god.
So what's my answer for this one?
You're good.
If you guys got lost, 0 plus 1 is 1, and anything to the 0 power is 1. So we can say, hey, they meet. So what's the end result? X plus 1 is fine, e to the x is fine, and they meet. There's no break. They meet. Continuous everywhere. Does that make sense? They only meet because their one-sided limits agree. I didn't think I had room to write limits, so that's why I just kind of did it as a sentence instead of as like a limit as x approaches. How about sine?
Yes.
Remember? Isn't he one of the nice ones? He just keeps on going. He has no vertical asymptotes, he has no breaks, he has no holes. Do you see how maybe the basic graphs can kind of help you on some of these guys? You can visualize it, be like, are there no vertical asymptotes, breaks, or holes? Sine's fine. Sine's fine. Who else is fine? Cosine. Who's not fine? Tangent, cosecant, secant, or cotangent. They have issues. Continuous everywhere but their vertical asymptotes. Okay, any questions before I turn the page? Could C have been discontinuous at 0? We had to check. But why was it not in this one?
Because C plus within.
They met. They met when we plugged in. Good. Alright. Let's talk about piecewise functions then. We had an example on the last page, and the AP guys love. I don't know if you want to have a special marker or highlighter just for AP type questions. I mean, they all are, but every now and then I get to point out to you guys that, yeah, they love asking you about continuity of piecewise. They love asking about continuity of piecewise functions. And we have some AP-ish questions. This one isn't necessarily an AP-ish question, but it is a piecewise function. We're going to kind of write about this just for a second. Continuity. We need to check the one-sided limits. And, now technically, the definition of continuous have 3 things, right?
Oh.
Limits are only one of those 3. So the one-sided limits are important. But technically, what else do we have to check besides the one-sided limits? The function value. The one-sided limits and the function value. At, and what do we call this little guy? The separator. Just my silly way of naming it. It might be a much more technical term, but it makes sense. It separates the pieces, right? Check the one-sided limits and the function value at the separator. Now, we just did this problem. I just want to go ahead and ask you guys, why did we not stress about the function value? We did do the limit as x approaches 0 from below. We checked to see if that equaled the limit as x approaches 0 from above. Why did we not think about or stress about the function value?
Because as we were checking the limit from below and above, we were essentially using the function values.
Good. If you only have 2 pieces, and as long as there is an or equal to on one of the pieces, the limit from below and the function value were the same one. So when we plugged into 0 plus 1, for this part, right? When we plugged into the top piece for negative 0.1. When we plugged into 0 from below, what were we in essence also doing? Yeah, plugging in 0 plus 1 is the function value because it's less than or equal to. So this little guy works for him and for him. So we technically did check it, we just didn't really say it. We did check it, we just didn't really say it. And then what did we do for this guy again? We plugged into e to the 0. Then what did we figure out at the end of the day? And we were good, right? So, in this piecewise function, it wasn't a big deal, but can anyone come up with, let's see if you guys can be creative. What would be an example of a piecewise function where this could make a difference? You guys think, I come up with examples all the time, but different. What would be an example of a piecewise function where you don't even have to have functions, just tell me what's going on with the inequalities. What kind of piecewise function would the third piece make a difference, the f of 0 or the f of the separator? What would change? Third piece. What would the third piece be? A point at separator. So how would the inequalities look? Like, this is our
Maybe just like a
danger, watch out for, right?
or just be a number.
Yeah, what if you had x less than 0? X greater than 0, and what would be the third piece? Then we have to plug into our f and our g and our h. Does that make sense? So this is where it's going to make a difference, where we have to check every single one. We're going to have to check this one from below, we're going to have to check this one from above, and we're going to have to check the at. Did it make a big difference here? No, there were only 2 pieces. The at was the same thing as the below, so it didn't make a big difference. But here, we would have to check every single one when we're checking for continuous. So we're looking for the continuity of the function, not a limit. For a limit, what would you plug into? Just the below and the above. That's it for a limit, right? A limit would ignore that. But for continuity, we have to check all 3. Does that make sense? So for continuity, we have to check all 3. For a limit, we'd only have to check 2. Does that kind of make sense? A limit only needs the below and above. Continuity needs the below and the above and the point. Let's see if we can get a more fun example. Ready? Set. Ooh. This is even a little bit different. The AP guys love to say something about continuity piecewise and find the variable that makes it work. I'm going to give you 60 seconds to write it down and think about how you would solve. They're saying, make this continuous. Don't stress about what you don't know, stress about what you do. Follow what we did in the other example. Maybe an equation will present itself that you can use to solve for A. Give me one second. Show some work. Not going to solve it for you yet, but I will show you my work because it's 60 seconds left. I won't solve it for you, but I will show you where I would start. And hopefully it would make sense to you. Why am I not stressing about the at, -1? It's the same as the above. Well, you guys take a second. Talk about it in groups. Maybe someone's already figured it out. How do you keep going from this? Go, talk it out. How do you keep going? And you don't have to do it mentally. You can write it down, make it equations.
You guys figure out, because you have to, for the,
Zach, talk to the group.
So that means the two functions are equal. And you plug it in.
Wait, I like that, except you didn't quite do it.
It made sense.
Keep the A general.
So,
How do we take the limit? Yeah, that's what Tyler's about to do. Plug it in.
A plus one. And then so you can
There shouldn't be an X in here.
yeah, it should be
So it's just A plus one. So it's 4 minus x squared is equal to ax squared plus 1. So then I plug the negative 1, which is equal to that.
You guys don't need an X in there anymore. Aren't you plugging in -1?
Yeah.
Aren't you plugging in?
Right? You could solve so you 3 plus A plus 1 is two.
A lot of you guys got stuck on the like, oh, there's something extra, I don't know what to do, but shouldn't you follow the same steps? Plug in -1 to the top piece for -1 below. Plug in -1 to the bottom piece for above. And what's going to naturally occur? An equation I can use to solve for A. Just naturally by following the flow. What did you guys get for the left side? 3, right? On the right side, you got A plus 1. Some of you guys figured out A was 2 other ways, but do you see how it's really just following the procedure? Come from below, plug into the bottom piece. Come from above, plug into the top piece. Once again, I'm not ignoring the definition of continuous, but the at is encapsulated in the above, so it's okay, I just didn't write it twice. A equals 2. Done, done, done. Does that make sense?
It's like a reflex of this.
I know, it's perfect. I like reflexes. And it keeps you awake. So, ready? Set.
Oh my gosh, we're doing something.
There's an M and a K.
Oh boy.
But it's okay. Follow the procedure. Except how many separators are there?
3.
2.
2.
3? Infinity. Okay, 2. I was right.
So what do you need to make sure works?
They have
Approaching 2. That's going to be 1 equation. What else are you going to have to be careful of? That's going to be another equation. And what do we do with 2 equations, 2 unknowns? System of equations or substitution, elimination. Go! You have to do it twice, with 2 and with -1. You want to find M and K. Poor little M, don't know why I forgot about him. I'm going to hide the screen. Check in your groups if you're doing the right thing. Hopefully you have one equation and you have another equation. What do you guys think?
Oh, it was the same.
Wait.
What do you think? Is that the right setup? Don't I need to worry about the 2 and the -1? So below 2, less than, I plugged into this piece. Plugged in what? I plugged in 2. That's the guy I'm talking about. And from above 2, where did I plug into? The other piece. So I'm plugging 2 into both his sides and setting them equal. But who else do I need to make sure is equal? So I'm going to plug -1 into both of his sides. And now I can compare. I reconcile. Yeah. Yeah. So think of it. I'm still doing the same process. Coming from below and above. But I have to do it for 2 and for -1, which is why I'm allowed to have 2 constants. I can have an m and a k. That's all right. I'm setting up 2 different equations. And if you guys notice, I'm going to start solving the one. Well, it's all either one. I'm just going to simplify them. This 2 plus 1 is 3. 4 plus 5 is 9. I'm just simplifying the equation, that's all. 2 plus 1 is 3, 4 plus 5 is 9. The other equation I have -2 minus 1, -3 plus 7 is, double check my math, 4. Equals 0 plus k.
That's fantastic.
That's fantastic, because I already got one. I already have one. What am I going to do with the other equation?
Plug the other one into something.
Plug it in, plug it in. Plug it in 4. Subtract from 4. K equals 4, M equals 3. Dun, dun, dun. Dun, dun. I'm going to circle instead of the box. Did it seem a whole lot harder than it ended up actually doing?
Yeah.
Yes. Do you see how a question and your confidence in working out the calculus can totally affect your ability to get to the answer? It's a struggle. It's a struggle. The AP is known for giving tricky questions, but the nice news is that we're going to see a lot of them before you ever get there, and hopefully learn how to approach them, and to be honest, learning the concepts to be like, oh, no big deal. Approach 2 from below and above. Plug in, approach -1 from below and above. Plug in, solve, solve, solve. Don't be afraid of things missing or pieces that you need to solve for. This is kind of a technicality. I'm going to write it fast. It's kind of a technicality. I'm just going to show you a quick example, so go ahead, feel free to write it. I'm just going to show you a quick example of how to apply it. In order for a function to be continuous on a closed interval, the definition kind of changes. Not a lot, but just a little bit. I want you guys to hit the graph and then just think about the intervals I'm about to state. There could be more than one. Which of the following is the function continuous? Could be more than one, could be all of them, could be none of them. The following graph, on which intervals is this function continuous? Yeah.
If on the graph it's the 5 versus children, and the middle part with the bubble, because it's a fact.
Only filled in on the top, not the bottom. If it was filled in on both, it wouldn't be a function, so I'd be in trouble.
What you said, you have on the bottom it says. That's confusing.
On which of the following, maybe that's a reason why or why not. Maybe that's a reason why or why not.
Oh, that's why it's not continuous, because it's only up there that it's 5.
So what you're struggling with is maybe a reason why you shouldn't circle that one. Does that make sense?
No, that makes sense.
I'm just
Kind of.
Okay. Question, is the function continuous from negative infinity to 2? 1. It's good, 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 good. Ooh, it's not good at 2 right here. And then there'd be a jump if it's right there, but am I caring about 2? I'm carrying, is it good everywhere up until but not including?
Yeah.
Okay. It's continuous there. What about from 2 to 5? It's good, and what does this allow me to say? At 2, does the limit exist?
Yeah.
Does the limit exist? No. But a closed interval, I only have to worry about from above. A closed interval, I'm not even looking on the other side of 2. I'm totally ignoring all of that. So just looking from above 2 and from below 5. That's what this is saying. On a closed interval, just look above the left endpoint and below the right endpoint. Is it good right here? Yeah, it's good. You don't look at 1.9, 1.99, 1.99. You're not even looking at that. It's not included. You're only looking on the in-between. From A to B, and a little bit above A. Ooh, that's not supposed to be an
I'm
A.
like, it's not.
That's supposed to be a B. It's a typo. I said B, and I didn't write it. There we go.
Oh, Miss T, now my notes
I
look
know.
ugly forever.
Oh, you can change an A into a B. Super easy.
Not mine.
Oh, not yours. How about C? Sarah, why does it not work?
Because 5 isn't.
Yeah. It's good, 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 up until, nope, that's bad. Doesn't exist there, so the limit would not agree with the point, because I'm including 5, so that one's a no. So the reason that you were asking is the reason that's a no.
Good job.
One thing.
Proud of you.
Does that kind of make sense? Okay, so it's a big old page, but what it means in actuality is, if I'm looking at a closed interval, only look in between, don't look on the outside. Okay? Last big idea. Last big idea. Hey, but we talked about it in pre-cal. Do you guys remember?
No.
Intermediate value theorem? We actually did. Doesn't mean you liked it when we saw it.
It's just like at a point, there's a point, it's weird.
Yeah.
It's all this complicated thing that means we're looking like that.
Does it mean nothing?
I mean,
It means just about nothing is what he's trying to say.
Does it mean just about nothing? We affectionately call it IVT. Intermediate value theorem. This is scorecard number 5.
is it actually?
Okay, definition continuous has some words, IDT has some words. I think I gave you this example last year, so as you write, I think I gave you this example last year. Let's see if you remember it. When I was born, actually I don't remember how long I was, never mind. At some point in my life, I was 2 feet tall, long, whatever. I was 2 feet tall. Do you believe me?
Yes.
Well,
Exactly.
Because there's no way I was born 2 feet tall. Okay. So at some point in my life, I was born 2 feet tall. How do you believe me?
Because you know that
You know how tall I am now.
you were shorter than that.
And you know when I was a baby, I was shorter than that. And height is a continuous function. It's IDT. If you know that babies are about this big, less than 2 feet. And then I'm this tall. IDT says I had to be every single height in between. So did I used to be 5'2"? Did I used to be 4'10"? Did I used to be 5'11"?
Yeah.
And 6'1"?
Yeah.
And 6'2"? I'm too tall. Alright, so IDT. Guys, tonight, get this in your forever card. There is one example we didn't get to. So maybe the very, very, very end of homework, something with IDT might get a little lost, but you should have the rest of homework fully attentive besides maybe IDT. Sound good? Alright, our goal tomorrow is to answer questions after finishing IDT and get into section 5. Bye, cool kids.